A radiosonde is a device that you can attach to a weather balloon and then you release it. And as it rises up in the atmosphere, it collects various meteorological data and then it transmits it back. Over the years, weather balloons have been mistaken for any number of things. Now we're going to use our balloon and fill it up with helium. Then we're going to let it go. It's going to go up to some altitude, and we want to know what the pressure of the helium gas is at this new altitude. There's a tremendous amount of information in this problem, so we need to start stepping through it and pulling out the information we need and parsing the problem. There are multiple gas law formulas to use in this section. So which one do you use? Well, I know my initial volume and my final volume, so volume's changing. I have an initial temperature and the final temperature, that's changing. And I have an initial pressure, and I want to know the final pressure. You see, that's why you want to step through the problem and look at the information, because based on this, pressure's changing, volume's changing, temperature's changing. That suggests that this is a combined gas law problem. Nothing was said about how much gas there is in the balloon. There are some distractors. The altitude is a distractor. You don't need that to solve the problem. I used it when I looked up information to use for the problem, but from a calculation point of view, it's not needed. Likewise, the helium is a distractor. You don't need it for the calculation, but I needed it when I set up the problem, because if I would have substituted in carbon dioxide, well, it wouldn't have affected your calculation. It would have affected whether this problem can actually work. Carbon dioxide is not a buoyant gas. It would not have floated. So the information. It doesn't matter which set of data you make set 1 and which set of data you make set 2, as long as you keep the appropriate information together. Look at the volume units. It's good, they're liters. You just got to make sure the units are the same. Temperature units, degrees Celsius. Well, you can't use Celsius in gas law problems. You have to use the Kelvin scale, the absolute scale. The reason why you're given Celsius in a lot of these problems is Celsius is a very common temperature unit. But you need to work with the absolute scale because you have to know where 0 really is, and you don't get that with Celsius. The offset from Celsius to Kelvin is 273.15. And since both of those Celsius temperatures go to 2 decimal places, I have to keep the 2 decimal places in my Kelvin temperature. And then the initial pressure is 1.000 atmospheres. We want the final pressure, and that's also in atmospheres. So we don't have any other unit conversions to worry about. Let me take the initial information away because I need some room to work. I've got the information laid out. We have the formula we need to work with. But what are we looking for? We're looking for the final pressure, P2. There are 2 common ways of working this out mathematically. You could plug in all the P1, V1, T1, etc. information into the combined gas law as it is, and then rearrange everything. I prefer not to do it that way. I prefer to take a formula that has variables in it and solve the formula for the needed variable first, and then plug everything in. In other words, like this. So the variable I want is P2 equals, and everything else is on the right-hand side. Because now, all I have to do is plug in my information. I will show you at the end of this podcast how you can take the combined gas law as it is, plug in the information, but you do need to do something to show your work properly. Now, top formula. I'll plug in my P1, my V1, and my T2. I'll plug in my T1 and my V2. Now my first check is a unit check. Liters cancel, temperature units cancel. I have units of atmospheres left. That's good because that's what I want. And there's my final pressure, 0.5334 atmospheres. Now, since pressure, volume, and temperature were all changing, I don't have an easy way to look at that final answer and think, yes, that's good, or no, that's not good. I think the best way to check this is plug everything back into the combined gas law. So let me do that. There's my P1, there's my V1, and there's my T1. Well, if I worked this problem correctly, then I should be able to plug in my P2, my V2, and my T2, and both sides should be approximately equal to each other. And ignoring units, because the units are the same on the left and the right, the left side is approximately equal to the right side. Now remember, I did say I was going to show you how you could plug the information in. Okay, so the method on the top, that was the way I preferred. So this other method, look down below. We have the combined gas law. You're looking for P2. So if we plug in all the information, what you can't do is you can't now just say P2 equals some answer. Because while it might be mathematically correct, if you do it that way, you're not showing your work properly. Remember, in chemistry, when we're doing calculations, your chemistry instructors are fanatical about making you show work. So in order to do this properly, we have to isolate P2, which means we have to multiply both sides by the reciprocal of that information in red. So now if you do that, whatever you do to the right side, recall that you have to do the same thing to the left side. And the bottom way is fine. I have a lot of students who like to do it that way. It's all right, but it's a personal preference in that there's just more writing. Either way, you have to show your work in your units. Nothing has changed about that.